Alright, you know what? You know what time it is? Stats time. Okay, so I was originally gonna break up correlation and regression and go way deeper into them than I usually do. But given the state of the world right now, and wanting to give you plenty of time to complete your exam, knowing that you may not have lots of access to a computer, or maybe you do, but some folks don't, and that's okay. So I want to give you plenty of time to work on your exam this week and to practice running stats if that's what you choose to do with those practice data sets. And you're welcome to come with questions on Thursday morning or to post questions in the discussion group. So, or to email me, but I'll just post them in the discussion group. Okay, excuse me. So, let's talk about correlation and linear regression. So with analysis of variance and t-tests, we were asking whether there was a difference between means. So it's all about differences, right? Whereas with correlation and regression, the framework is now all about relationships. Okay, is there an association between x and y variables? Is there a relationship between your x and y variables? All right, cool. So remember, with one-way analysis of variance, you have a single continuous response variable and a single categorical predictor variable, right? And we're actually going to get into multi-factor ANOVA or two-way. We'll go up to two-way ANOVA next week, and there you'll have multiple categories, but for now we're just sticking with the single one. So with correlation and regression for both of them, you have a single continuous response variable and a single continuous predictor variable. And depending on what your question is and your data, you might use a correlation or a regression. Okay, and we're going to talk about why you might use each one here in just a sec. Because you're going to have to choose. Like I'll say, here's a study, and we're interested in this question. How do you answer it statistically? Right? So a correlation and a regression are not the same thing. That's an important thing to point out. And it's important to watch your language when you're talking about correlation. Watch your language. People will often say, even with analysis of variance or t-tests, they'll say there was not a correlation, there was not a significant correlation, or there was, when really they're talking about differences. A correlation refers to a correlation. All right, so if you ran a correlation, you say correlate. I ran a correlation. There is a correlation. I shy away. I tend to encourage people, don't say correlation unless that's what you ran. Okay. If you ran a regression and you say, oh, there's an association of some point, it could be, you could say there's an association, or I like to say there's a relationship, because that's what that is showing you. Okay. So the difference between a correlation and a regression, correlations are essentially just telling you if two variables vary together. There is an association between two random variables. Okay, so x and y. All right. With a regression, you are looking at particularly a linear relationship between a response variable and a predictor variable. The response variable is your y variable, or your dependent variable, and your predictor variable is your x variable, or your predictor. I just said that. Independent variable. That's what I mean. All right. And when you run a regression, a regression line is drawn, and we'll get more into that in a second and what that means and what regression actually does and what this line is actually about. Okay. But with a regression, you'll actually have your linear regression draws a line. Okay. The correlation doesn't do that. So regression is really useful and very it's powerful for a lot of uses. I just said that it was useful. Man, I can't teach today, I guess. It's so hard teaching to a computer. Do you know how hard it is? I'm staring at a dot. Okay. Anyway. So, regressions are really useful, though, if you want to do things like make a prediction. If you have a significant regression, you can reasonably predict a value in y based on a value from x. Now, there are some caveats to that, which we're going to talk about in a little bit, but that is one of the functions of regression is you can make predictions, all right? It also provides evidence of a functional relationship, cause and effect. You can reasonably infer cause and effect from a regression relationship where you can't do that from a correlation. Maybe you've heard the term, or the adage, not the term, the adage, correlation doesn't equal causation. That's right. Correlation is just, does X vary with Y? Regression, though, can infer causation because it can actually provide evidence of a cause and effect relationship between X as your cause and Y as your effect. Okay, cool. So let's talk about assumptions of these tests. So most of them are pretty similar to what you've seen in the other general linear models, but a few differences. So the first is bivariate normality. So you have been testing univariate normality, right? Normality of your response variable, and not of your predictor, which makes sense because they've been categorical. But here you have two continuous numeric variables, so you need to test for bivariate normality. That means that you check to make sure that x is normal and y is normal, okay? And you did that the same way we've been doing it with histograms and normal QQ plots, all right? You could run our Shapiro-Wilk test. So that's the first assumption, is bivariate normality. Correlation assumes that the data are independent, all right? Just as you've seen before with many of the tests that we've done. Linearity. So this is where you actually create a scatter plot of your data with x and y, and you check to see if the data create a linear relationship or not. So here I'm showing you a rough linear, well, that's pretty good actually, linear relationship there on the far left, and then nonlinear relationships there on the right. So if you saw that, if you see data that are nonlinear like that, what you would do is log transform the data. And when you do that, you have to be careful because now if you're doing correlation or regression, you always have to think in terms of bivariate activities, or what you're going to do has to be bivariate. So if you log transform the data or square root transform the data, you need to transform the x variable and the y variable, and then reassess the assumptions, okay? So that is one assumption of this test. And then homoscedasticity, so you have to check to make sure your variances are roughly equal, but there's a different way to do that. Because since you don't have categorical predictors now, you might be like, wait a minute, how am I supposed to do that? There's no, there's the box plots and what? I'm going to show you how we do that, okay? So I'll show you how to that we do that next Tuesday when we do this in R. All right, cool. So arguably, I shouldn't say it's the most common, but the one you'll probably see most often, it probably is the most common, is Pearsons product moment correlation, okay? And you get a correlation coefficient from that. All of these correlations that I'm going to show you three kinds. Oh, okay, she just moved. It was a scary noise. Okay. So I'm going to show you three kinds of correlations, and you get some sort of coefficient with each one. This one, the Pearsons correlation coefficient, is a little r. So your r value is essentially telling you the degree of correlation between your variables, and it ranges from -1 to +1. All right. So -1, that means you have a negative association, whereas x increases, y decreases. If you have a close to +1, then as x increases, y also increases. It's a positive association, all right? So that's what that sign actually indicates. And the null hypothesis in a correlation model, a Pearson correlation, is that your R value, your correlation coefficient, is 0. That is no correlation between the variables. Now down here I have the formula to calculate a correlation coefficient. I'm not going to make you do this by hand in this class right now, but maybe you can do it for bonus points. So, and it's called the product moment correlation coefficient because you're taking products, right? So it's actually a pretty simple procedure to calculate your correlation coefficient. You just multiply each x point by y and sum them. So x times y, and then take that over the square root of the sum of all of the x values squared times the sum of all the y values squared. Okay. So not too difficult to calculate, but at this point in the semester, I really just am interested in you running it in R and interpreting the output correctly. All right, and checking your assumptions before you do that. Cool. So there are alternatives. If you have data that violate the assumptions of a Pearsons correlation, you have a few options. The first option is to transform both variables and then check your assumptions again and run the Pearsons if it works, okay, because sometimes it does. If your data still do not meet the assumptions of a Pearsons correlation, you can run two different kinds of correlations that don't have the same assumptions. Essentially, as intro statisticians, I'm just going to tell you these don't have the same assumptions, and so if your data are not normal or nonlinear, you might check these out. And I'm going to give you code for these, all right? So you could decide whether or not to use them. There's Spearman's rho, and rho refers to the name of the coefficient that is calculated that tells you the degree of association. So the Pearson correlation, it's an R. Spearman, it's a rho. And this test is particularly good with outliers. Okay, so if you have outliers in your data set, what Spearman's rho does is it's a ranked correlation analysis. So it basically ranks your data. Okay, and Kendall's taw is not as powerful, but it can detect nonlinear relationships, so it can be helpful in that situation. So, oh, I skipped ahead. That's not what we want. All right, there we go. All right, so let's talk about reading a correlation table or correlation output. I'm going to show you this next week, but just briefly. So you'll get an output that looks something like this. This is what you would get from R. And so I've highlighted in red what you're really super interested in here. Okay, it gives you your confidence interval, which you know about, right? But what you're really interested in here is your correlation coefficient, which is at the bottom. So this one is 0.41 and positive 0.41. Let's point that out. And your p-value is 0.0003, which means that there is definitely a positive association between these two variables. So this brings up an important point, and that is sometimes you have a correlation coefficient that you might say doesn't seem very high, like 0.4 out of, from 0 to 1, 0.41. But it is a significant correlation. And this particularly is not that uncommon in ecological data because nature can be very noisy, and so you may have a correlation coefficient that's somewhat we would think of as low or like maybe less than 0.5, but it's still a significant association, okay? So that's something to keep in mind. You can also you can sometimes have a pretty high R value and not have a significant correlation, okay? So just bear that in mind. Just because you have a high R value does not necessarily mean you're going to have a low p-value, and just because you have a low p-value, doesn't mean that you're going to find a correlation all the time, okay, or a very strong high correlation coefficient. Cool. I think I just did the same thing two ways. It's late. So that's how you read that. All right, and this actually, what's nice is it tells you the direction. So you could just from this output say there is a significant positive association between area of this plot and plot cover. Okay, cool. So that's how you would report that. And I'll show you on Tuesday how you actually show your R value and your P value. It's very similar to how we report an F statistic and a P value in that you'll put like R equals and the value, comma, P value. Okay, so, but I'll show you that Tuesday. All right, I did also want to show you this. This is actually an output from Excel. Excel can run correlations, and I know you're all cursing me right now, like, why aren't we using Excel? Because R is very powerful and useful, and some of you will use R again. It's a good skill to have. So, but here you see, here's the correlation coefficient. However, Excel, just the correlation itself doesn't tell you, give you a p-value. Okay, so be advised. All right, that's all I want to tell you about correlations today. It's a measure of association between variables. Your R value gives that you an indicator of, the strength of that that association. And it's expected to be linear if you're doing a Pearsons correlation, right? But let's move on to simple linear regression. Okay, so simple linear regression, and it's called simple linear regression because you have one x variable and one y variable, as opposed to multiple linear regression, where you have potentially multiple predictors explaining variation in a response variable. Okay, so linear regression is used to detect linear relationship, a linear relationship or linear relationships between single continuous response variables and a continuous predictor. All right, so why might you use a linear regression? Well, if you have a few different aims. If you are interested in predicting y in your, predicting a value in your response from x, your predictor, you could potentially use a linear regression. If you get a significant regression model, then you could feasibly, there are some caveats, which we'll talk about in a minute, predict y from x. Okay, cool. You may also be interested in describing variation between y and x, or trying to figure out how much variation in your response variable is explained by your predictor. Okay, how does your predictor, does it influence y? Right? Does it influence your response? Is there some sort of causal relationship? You can actually infer functional and causal relationships from a regression. But there, you do have to be careful. But you can say, it's more, you can be more confident in that than if you were running a correlation. You could not say that you could predict y from x, right? It's not appropriate to do so with a correlation, all right? The null model here, now those of you who learned y equals mx plus b for the equation of a line probably remember b is the y-intercept, but here we don't want to confuse you, but you typically will see the equation as y equals a plus bx, okay? So your null is that the slope of the regression line is 0, okay? And rather than a correlation coefficient, the linear regression provides a coefficient of determination, which is an r-squared value. And so this r-squared value essentially tells you it's always positive because it's a squared value, and it essentially tells you the amount of variation in y explained by x. And you could even express it as a percentage. So for example, if you get an r-squared value that's like 0.73, and you could say that x, whatever variable x was, explains 73% of the variation in y. Okay? And this is just right here just to show you direction of relationships, because here's an important thing. Since r squared is always positive, it does not tell you the direction of the relationship. You must look at the data and you must report the direction of that relationship, because that's your trend, right? I always tell you, report your trends, when you do an ANOVA. What's bigger versus, smaller, right, after you run your post hocs, or in a t-test, what's the larger versus the smaller of whatever means you're testing, right? You want to provide information about what the data actually look like, not just, oh, there's a relationship, or there's not a relationship. I mean, if there's not a relationship, there's not a relationship. But sometimes you may have a trend even then. So just be sure when you run a regression that you are clear and tell your audience. If there is a significant regression model, and your p-value is less than your alpha, then you should tell your audience, sorry, my foot hurt, that you have a positive or negative relationship between the variables. Okay, give some hint, give some information about the direction of that relationship. Okay, and basically what regression is doing is minimizing residual variation. So let's see if I have it here. Yeah, so it's fitting a line to minimize the residuals. And remember, I've taught you what a residual is, right? So if you have a regression line here, the residual is essentially how far these data points deviate from that line. Okay, so let's see. This is just showing you, this is from Quinn and Keogh, which is one of your optional books for this course. Okay, and it's showing you here, these two actually have identical regression lines. All right, but the differences between observed and predicted observations here are greater. All right, and so basically what's happening in a regression is it's actually running an ANOVA model and looking at the variance between the variance explained by your predictor variable versus the residual variation. Okay, interesting, right? So again, it's fitting a line with the lowest residuals. So here you have, right, how far those data points deviate from that line. All right, and just to remind you here, your regression equation is y equals a plus bx, where b, your null is b is 0. So this is the slope of your line, this is your x-intercept, and this is your y-intercept. Okay. Yep. Okay. So let's talk about the math here a little bit. So I'm not going to spend a lot of time harping on this because the main point in this intro stats course is just for you to understand what regression is doing and when to use it and how to interpret it. The same with correlation. Okay, but this is showing you data points from which you might calculate a regression line. All right, so essentially what's happening is the residuals, here's your mean for your y and your mean for your x, and basically it is calculating and minimizing residuals between those. Okay, cool. And so here is how you would do that. Sum of the cross products over the sum of squares for x, but I'm not going to make you do it by hand. I'm not going to make you do a regression line or anything like that by hand. I just want you to be aware of it. So if you go on in statistics, you'll go farther into this. Okay. Okay. So assumptions in linear regression. Oh, yay! So they're the same as you would use for like a Pearsons correlation. So independence, homogeneity of variances, linearity, and normality. Okay? Yay! All right. So, and this here, actually, again, this is from Quinn and Keogh, which is a really helpful book. If you're going to go on in stats or to go to grad school or anything like that, that's the book that actually we used when I was in graduate school. So I highly recommend it. All right. So these are residual plots, and this is one of the ways that we can test assumptions of linear regression. All right. So here, this is a residuals versus predicted plot. Okay. So essentially, what it's telling you is this is one of the ways that we can assess like normality, and I'm going to also show you how to assess homogeneity of variances when we do this in R. But what you're looking for, you don't, and so this is going to show you like the variance in your data, right? So this is nice. It's pretty even, good spread. Okay. This, you do not want wedge-shaped. This is actually showing you essentially where you would have a skewed distribution. So you don't want wedge-shaped residuals versus predicted plots when you're doing a linear regression. Okay, and I'm going to go over this a lot more when we actually are looking at it in R, but I just want to introduce it to you today. All right, so like this is showing you this is spread pretty evenly around the line, so pretty nice there. But here, not spread so well around the line, okay? Or, well, it's spread farther, right? So you get this wedge shape, which is not so great, all right? These are data that you would want to potentially transform both variables. All right, so a few pointers. Look, man, it's too easy. Okay, with the dotted one. Okay, so we'll move on. Thou shalt not extrapolate beyond the range of your data. This is really important, especially when you're trying to predict y from x, okay? You cannot use regression equations. So when I say a regression equation, the regression line that is drawn through your data that the program will give you, basically. But if you want, I could show you how to calculate. You get an equation, and that equation allows you to predict y from x because you're basically just solving, right? Based on whatever value of x you have, you use the slope and the y-intercept, and you can actually solve for your y value, right? However, you cannot use that equation to predict y from x outside the range of your observations. So what that means is, and I wish I had a chalkboard right now. So if I am interested in predicting a certain value of y, but I only have x values up to, like, let's say I have x values and y values up to, like, and it's not giving you any information about the scale, but let's just say I have, 300 milligrams of something, right? And I want to predict y, but I want to predict it for, like, 500 milligrams. Like, you can't extrapolate past your data. That line is only valid for as far as your data go. Okay? So where your last data point lies, you can't extrapolate beyond that. Okay? That's why, like, when we make standard curves, like if you're creating a standard curve to determine the concentration of an unknown in a chemistry lab or in my lab, we have to have standards that account for every potential absorbance value that we're going to get for an unknown. Because if we get an unknown value that's bigger and its absorbance is bigger than any of our knowns, we can't extrapolate that far. We have to have a standard that goes higher than that, so that it's within the range of the data. Okay, so you cannot extrapolate beyond the range of your data. All right. Also, linear regression is only appropriate when a straight line is appropriate, when it's linear. All right, and it should be that you should have the same number of points above and below your line. Okay, cool. So these are just just to give you an idea of different kinds of regressions and what they might look like. Okay, so, oh no, these are R values. So this is going to be, all right, so correlation, Terry. So this is a perfect where you have your R value is 1, so like very closely associated, right? All right, so this is a correlation. Here, 0.5. So this is just to get you familiar with kind of how data would look with various R values, okay? And it's also giving you the slope, all right? Here, R equals 0. So this is, and B equals 0. So this is the null model, essentially, all right? Cool. Here you have a negative slope for the regression. Oh, yeah, it's showing you for regression slope, but the R value is also negative 0.8. So there is a little bit of spread, but it's really high. So you can just kind of see how these fall out close to a line, right? Okay. So determining significance and interpreting results. And I'm going to go through this in R on Tuesday, but just to introduce you to it, what you're going to be interested in is really at the bottom. And so you're going to be looking at your R squared, and I'll talk about multiple and adjusted R squareds on Tuesday, but you also have your p-value, right? So the correlation that I showed you last time, this is, I think that's not the same as, it's set correlation data. So that is essentially just showing you that there is a significant relationship between the two variables, but that x does not explain very much of the variation in y, right? You see this R squared This is the multiple R squared, and the adjusted R squared, which is adjusted for your number of predictors in the model. So 0.16 is not very high because R squared ranges from 0 to 1. So pretty low, but you still have a significant regression there. Okay, cool. All right, so how to interpret your results. Always report your R if you're doing a correlation, or your rho if you're doing a Spearman's rho, or a tau if you're doing a Kendall's tau. Those are all those coefficients. Or your R squared, your coefficient of determination if it's a linear regression, your p-value, and the direction of the trend. All right, and remember, and this is true not just for linear regression and correlation. This is true for your test you're going to take this week. This is true for any statistical analysis you're going to run. It always comes back to what is your question? What is the research question? Always bring it back to what was the question we were trying to answer, and then frame it in that context, okay? And be careful with your language. So you know, if you ran a correlation, you can say you ran a correlation. But if you didn't run a correlation, be careful with the use of that word. Okay. Also, I've seen people say in courses, not like in publications, you won't see this, but you know, there was a significant difference if their p-value is less than their alpha. They say there's a significant difference. It's a relationship. Remember, correlations and regressions are all about relationships. So you should use relational language. There was an association. There was a relationship. Y varied with X in this way. There, you know, as X increased, Y did as well, or what have you. Okay, so just be careful and word your responses and your explanation of your data and your interpretation of your statistics thoughtfully, which you should do anyway. Okay? That's it. Man, classes are a lot shorter now that they're online. Well, at least my lectures. It's because I'm not there to. There's not as many. It's just jokes don't come to me when I'm staring at a computer. Anyway, oh. So I just realized also you're looking at one of my favorite dudes. So if you don't know who this is, you need to ask me, because actually you should look him up. This is Carl Sagan. So he's not really like part of this class, but he was an astronomer, and he was Lynn Margulis's husband, well, first husband. So he was Cosmos. If you see Cosmos, like with Neil deGrasse Tyson, there was an original Cosmos, and it was Carl Sagan. Carl Sagan is like one of my heroes in science. So anyway, you should look him up. He was like the coolest ever. So let me know if you have questions about correlation and regression. You can put it in the discussion board. You could ask it on Thursday if you want, and I will see you all soon. Just a reminder, so Thursday, I'm not going to post a lecture for Thursday. Just work on your tests this week. Turn in your post-talks. Thank you, Addie, for reminding me. My eyes were crossing and being tired from being in the field all weekend, so somehow that slipped me. But I want to give you the points. You've earned them. And then next week, pretty much we're going to mostly be in R, but I am going to post a brief talk about multi-factor ANOVA just to give you some guidance about it so that you understand it, because it's really important to understand it, because then we're going to be dealing with things like interactions, which just wait. All right. So, all right. Good luck on your test. Let me know if you need anything, because I'm here for you. Oh, yep. Oh, my dog.